lecture. So here in the previous lecture, what we have seen is we looked at the basic idea of taking charge across a capacitor, and if that charge is greater than 0, we should make an attempt to increase the value. If the charge is less than 0, we should make an attempt to decrease the value. And the simple idea is we can use a voltage controlled current source which can push current into the node depending on the voltage delta V, or push current out of the node depending on the voltage delta V. And by by analyzing the circuit, we understood that the concept, what the presented concept is an unstable system basically, and that works on a positive feedback mechanism. And we looked at this factor as a gain, the regeneration gain for a particular period, and the resolution, the maximum, the minimum resolvable voltage can be made, or we can work on the resolution by only by working with the time constant, which is in turn depending on C and GM. And so the resolution made is, or the conclusion what we made is, C should be made as small as possible, or in turn C cannot be an explicit capacitor, rather we should actually use the parasitic capacitance of the devices. All right, so there we continue. All right, so what we'll do now is we have the circuit structure available now as a capacitor and a stage which can give this current over here, right? And this is the single-ended version, right? But these days, or when we talk about ICs, integrated circuits, everything is differential. Nothing is measured as absolute, rather we always go for differential circuit, right? And the moment we say differential, the meaning is you'll have two voltages, say you'll have V1 and say V2, and what we do is we'll have a common mode voltage and a difference voltage. So V1 minus V2 by 2. The common mode voltage will be same, minus V1 minus V2 by 2. This is what we generally represent, right? So where this forms here the VCM value, common mode voltage, and this represents the differential voltage, VD, right? So if you have two voltages, say V1 and V2, how we generally represent this? We represent it as the common mode voltage plus D, or we represent common mode voltage minus VD, right? For the obvious reasons why we go for differential. This is what we generally do in an IC, right? Differential signaling is something like this. Now and why, if you're asking me the question why differential, the reason is again obvious, right? What is the reason why we go for differential circuits in ICs? Can I get some response? Yeah, to cancel noise. Obvious reason is to cancel noise, because all these circuits, or all the analog circuits, will be on the same chip, along with so many other digital counterparts, where you will have the clocks will be quickly, shift, like clock transition will be high. That will in turn give a lot of noise to the signals here. So that is the reason why we go for differential signaling. So the advantage is actually noise can be eliminated, right? So now with the discussed single-ended version of a form of comparator, what we discussed now let us see how we can develop this to a differential one. So previously, if you are looking for a voltage delta V which is greater than 0 or less than 0, now what I need is, if your voltage is, say, from a common mode voltage, if you have VCM plus VCM plus VD, or if you have VCM minus VD, the whole task is to determine whether this VD is greater than 0 or VD is less than 0. Does it make sense? Just moving from the single-ended version to a differential version. Now, since we have the single-ended version in our with us, how can we think about developing a differential structure for the same? So the differential version, in order to get a differential version, what we can do is, the idea remains same. Um, so now we have two voltages. No, one is VCM plus delta V, that is VCM plus VD on this capacitor. On the other capacitor, I have VCM minus VD. Right. Now, since I am looking for a differential circuit, there should be a controlled voltage controlled current source which can push current into this node as well as this node. So how it should be? If your VD is positive, so if this voltage, if this is going up, your GMVD should flow in this direction. At the same time, yeah, even here also this side, because um, current should flow to this node and current should be pushed to this node and it should be taken away from the other node, right? So if your VD goes high, the current will be taken to this node. Now can you think about a simple circuit which can perform this operation? If you have, if your input voltage is greater than a threshold, or like if you have a threshold, if it is greater than threshold, you should actually get an output which can act a kind of a regeneration. What I can use in order to get the structure? Any idea? So the task is this: if this node voltage goes up, the current should be pushed into this node. The other way, if it is low, it should be pushed out of the node. That is a task we need to have. And the simplest circuit what we can think is only a simple inverter, where I have this capacitor here. Now that voltage will be sensed here. All right, so this voltage is VCM plus VD, and this is VCM minus VD. Now if I simply connect an inverter from this node to this node, will it serve the purpose? What I need here is, if this VD is positive, this node should eventually regenerate and go to the VDD or the high voltage or 1. At the same time, if this voltage is smaller, this should actually go to 0. What I should do here? The simplest thing what I can think about is an inverter, but just using one inverter in this will not help, because depending on this voltage should in turn increase, or I should actually create a positive feedback mechanism. So what I should do is, I should sense the other node as well by connecting one more inverter in this fashion and then connecting back to this. Will this work for the mentioned task? Will this work? What do you think? If VD goes up, what will happen? This inverter, this will be triggered. If this VD goes up, now we should think that the VCM voltage or the common mode voltage, what we say, should be the switching threshold of the inverter, right? So now if your VD goes up than the threshold, what will happen? This will go low, and that will trigger this will go high. Ultimately, this node will go to a high voltage. At the same time, this node will actually go to a low voltage. Does it make sense? So if VD is greater than 0, the same node, the node VCM plus VD, will go higher and higher. Can I get some response in the chat? Are you guys with me? All right. Okay. Let us look at the circuit part, which will be a little more easy for you guys to connect. So what I can do is this back-to-back inverter. I have one inverter, like two inverters connected back to back. So what I will do here is two inverters connected back to back. So this is one inverter. This is another one. Now it is connected back to back, right? So if you look at this, the output of the first inverter, say I'll call this as inverter 1 and inverter 2, the output of first is connected to the input of the second. So the output of first is this, so that should be connected to the input of the second, and the output of the second is converted to the input of first. So this is the output of the second one, which should be connected to the input of the second, right? This is what the structure what we have, right? And when you have two inverters connected back to back in this form, we often call this as a latch. All right. So what do you think? Will this work for the purpose what we have discussed so far? Say I am just connecting this to VSS and this is connected to VDD. What I need here is, as mentioned before, we will not use any explicit capacitors. Rather, the voltages will be stored on the nodal capacitance or the parasitic capacitance itself, right? So what do you think? How can I make this comparison to happen? So I can I directly connect the input here? Can I directly do that? So can I connect this into VCM plus VD and this as VCM minus VD? Will this work? Will this work? What do you think? Will this work? Yes or no? This is the structure what we have. Back-to-back inverters, and the nodal capacitance, the parasitic capacitance of that node is marked as an explicit capacitance before, but now that is not an explicit capacitor. Yeah, we should check voltage levels. All right. Yeah, before checking that, see if I am connecting directly the voltage which I need to check or to make a decision directly to this node. You see, one node is VCM plus VD and other node is VCM minus VD, and I'm actually directly tying the two voltages to two nodes. It can make a decision or not, but how will I? But this cannot be done like just by directly connecting this voltage to the connecting the voltage to make a decision to the node. Rather, this will work based on a clock, right? Because we have a sample and hold circuit where it works on a clock. So when the clock is high, we have a voltage coming in, and at the sampling instant we have the voltage which is stored across the capacitor, or that is the voltage what we have, right? So we will not directly connect this to these two nodes. Rather, we will actually connect this using a switch, right? So here we connect the voltage VCM plus VD, and here we connect VCM minus VD, and this is a switch. Let me mark it as phi 1. Phi 1 is a clock. Are you getting? Right. So now this back-to-back inverters, when will this this back-to-back inverter, or we call this as the entire thing as latch, when will this latch sample the data, or what is the sampling instant? Say, let me just draw the clock signal here. Say this is phi 1, and say you have a, this is the signal what we have. Can you tell me what is the sampling instant here? Sampling instant, what do you mean by sampling instant? So what voltage the latch is going to regenerate, or what voltage this latch is going to work and make a decision. So when the clock is high, phi 1 is high, at the falling instant of this phi 1 clock, whatever value is there, that is the value which is actually taken, right? So latch samples at the falling edge of the this clock phi 1. So this is basically the sampling instant. So whatever is the value at the falling edge of this clock, that value will be available in the capacitor, and on that this should make a decision whether it should go to a high value or to a low value, right? Now are you guys with me? Can I get some response? Okay, so now when you have a clock here, and when these switches, the switches, say you have two switches, right, on the left and right, when these two switches are closed, or during phi 1, right, these switches are closed during phi 1. Yeah, so now when the switch is closed during phi 1, so what do you think? The inverter should continuously work on the signals coming in, or it should actually work on basically on the voltage which is available at some time? Yeah. Sriniket, I'm getting your question is, isn't the latch level triggered? Yeah. Generally, when you say a latch, it is level triggered. But now you see, in this specific case, if I'm allowing this to work on that, what I meant by that is, say when your phi 1 is high, during this entire time, when your phi 1 is high, yeah. First of all, tell me when your phi 1 is high. Uh, what I need here is, I need to get the value on the nodal capacitors here, right? Say I have two capacitors here, and I should get some value in the nodal capacitor. Then only the inverter can actually work and regenerate it, right? So first of all, whenever the sampling process happening, or whenever the value is getting stored on this capacitor, inverter should not actually operate. Now, are you getting that? If the inverters are keep on operating, so I say initially during phi 1, initially some voltage is coming. Now inverter started regenerating. So how it is regenerating? It is actually regenerating in the same node itself. So now I don't think the entire data, or this node, if it is the if we are allowing the inverters to regenerate during the entire time of phi 1, the data cannot be properly coupled to the capacitors. Do you agree to that? Yes. So what we should do here is, say we have, let me just draw it here. I'll come back. Navishri, I think I can come back to your question now. Let me just explain this. So this is what we have. This is back-to-back inverters what we have. And at this node, we are assuming that the internal capacitors are available. Now we are taking the help of this back-to-back inverter to regenerate the value and to make a decision based on the value which is available in the capacitor, right? Now for the back-to-back inverters to make a decision or to start the regeneration process, there should be a fixed data available. There should be data available on the capacitor, right? Now that is why initially we are actually connecting two switches here. and I'm giving the data here as say VCM plus VD, where VCM is the switching threshold of the inverter itself, so that when the voltage is coming slightly more than that, it can actually start the regeneration process. On this side it is VCM minus VD, and this works on phi 1, clock phi 1. Now whenever phi 1 is high, the data is actually coming across a capacitor, and we also mentioned that the sampling instant is the falling edge. So why I said that the sampling instant is falling edge is because I cannot make, or I cannot allow the inverter to start the regeneration process during the entire time of phi 1, because that will not make any sense, because I am trying to connect a data and the inverter is operating on the data, and this node will be already in regeneration process, right? So what I should do here is during phi 1 or when, so when the phi 1 clock, when phi 1 is high, what I should do is inverter should be basically disabled. Inverter should be disabled, right? Why it should be disabled? Now at the end of clock phi 1, whatever data is there, based on that data, the positive feedback or the inverters back to back should work and make a decision based on the data. That is why I mentioned that this is the sampling instant. Sampling instant is at the edge of the clock, and that value will be stored in the capacitor, and after that only we should make the inverters enabled. Till then inverters should be disabled. Does it make sense with respect to the circuit? Then only the circuit can operate properly, right? Yeah, I think somebody is having a question. Yes, yeah, that is what I'm going to do that. So now in this mode this cannot work, because I think that is clear. That is a point what I want to make it clear. In this mode the circuit cannot work properly. So for that reason what I should do is during the sampling time, or whenever the phi 1 is high, I should make inverter disabled. How can I make inverter disabled? I can do that by connecting. There are different, by the way, there are different methods to make it disabled. One method is, let me draw in the new page. So we have right, this is the inverter. Now the input of this is connected to output. This is connected here. Now we have this switch which works on phi 1, and during phi 1 inverter should be disabled, and that can be done by actually connecting another switch here. Here I call this as phi 2. Now this is your VCM plus VD, and this is VCM minus VD. Inverters can be disabled in multiple ways, but in this case the entire inverter is is disabled, and there is no current. This can actually save a lot of power as well. This is yeah, this is the circuit. I will not say this is the final circuit, but yeah, with this we can actually think about how a comparison is made and how the voltage is getting regenerated. Right now, so look at this. Now during phi 1, during phi 1, whatever voltage is there, the sampling instant is the falling edge, so that voltage will be available across at this node, this nodal capacitance. And when the phi 1 goes low, and after that only, so by the way phi 1 and phi 2 should be are non-overlapping clocks. What do you mean by non-overlapping clocks? What do you mean by non-overlapping clocks? Both are not high at the same time. Two clocks both cannot be high at the same time. By the way, this clock is what exactly needed in this one. We discussed about bootstrap switch, right? Wherever we use 5152, in all those places we need this non-overlapping clocks only. And we did not discuss about circuit which can generate non-overlapping clock there. There are different circuits available, and the simplest one is, let me just draw it here. The simplest circuit is actually, you can, and this is how we will have a very simple non-overlapping clock generator, where you will give an input here which can give you phi 1 and phi 2. Now why this additional inverters here is, say for example you want an advanced clock of this phi 1, you can actually take from here. Similarly, if you want an advanced version of phi 2, you can actually take from here. This is one simple circuit which can give you non-overlapping clocks. So if you look at this phi 1 and phi 2, it will be like this. Yeah, both will not have on time together. Both the clocks will not be high during the same time. Yeah. Yeah, so this is about non-overlapping clock. Now yeah, so this is the circuit what we have. This is the final circuit what we have for now, which can do comparison and make a decision, and the decision is made based on the regeneration which will happen between the back-to-back inverters which is connected. Alright, so what I will do is I'll wind up for today, and tomorrow we will see the operation of this, or how comparison is made on this latch with waveforms. With waveforms we will see in next tomorrow's class. Alright, so now if you have any questions, we can actually have discussion.